and it's starting. Remember that when I broadcast it to YouTube, there is a lag of about 3-4 seconds deliberately. So you'll be 3-4 seconds behind. Now, how do I get the URL? Okay. So I should be posting it to the class Slack. Uh, Kate, did you solve? I trust you have solved the problem of your Zoom, isn't it?
Yes, it's because I opted for the Google login with Zoom,
Yeah.
and it's a bug on their part because if you try to log in later through certain screens, it only gives you the email and password option to log in, which isn't valid if you use Google. So I just make sure to log in directly to the Zoom ahead of time using Google, and then
Oh,
I put that in.
okay. Nice. I guess all is well that ends well.
Yeah, I got
Nice
it
to
figured
see
out.
you. Nice to see you out of the struggles with that. All right, guys, we are starting the recording and we are starting the session. So welcome back. We were discussing this week to a class of algorithms in neural network or an approach that I call the bottleneck method. This word is not called like that. So, but to me, it seems to all be based on the fact that if you pinch down a neural network in its flow in a hidden layer, it is forced to somehow summarize the information or extract the essence of the information. So, in that spirit, we talked about a few things. We talked about, for example, principal component analysis, and we realized that it's a special case of doing something like this. I'll review what we did. We said that these, all of these neural networks, they have a certain structure. The structure is that you can compress things down to a much lower dimensional representation. I use the word Z for the lower dimensional representation and X or the initial vector space as X, which is a much higher dimensional space. One example that we took, which is the singular value decomposition, would be that. So in singular value decomposition, you just do SVD, LSI, latent semantic indexing, you do singular value decomposition. The same idea carries forward to this bottleneck algorithm. The only difference is singular value decomposition is inherently a linear method, whereas we are generalizing this now to more complicated situations. It need not be like that. It may be more complicated than that. So, and sometimes linear is good enough. For example, today we are going to talk about something called word embeddings. It turns out that they are mostly linear. The sort of bottleneck you create is through a linear transform, a matrix multiplication, and you don't apply in the hidden layer much. You don't apply an activation function at all. So it's a hidden layer. The input layer, the hidden layer, the output layer. The input layer is pinched. It's a bottleneck, and usually you do or do not apply activation based on situation. But for word embeddings, things that we're going to talk about, you don't apply an activation. You just do a straightforward um, matrix kind of a multiplication. So now we'll learn a little bit more about it. When you create an architecture like this, you give it an input and you give it an output. You these things are, for example, examples of these are autoencoders. That is one example we did, and we did the variational autoencoders. Principal component analysis, it turns out, is also another example of it. If, for example, you do take the data in, try to do a linear lower dimensional representation of it, and then you project it back to the original data, what will happen is, so long as you don't apply a activation function, or another way of saying it is, so long as you apply an identity activation function, you will essentially recover PCA, right? Because a PCA is literally that you take the input and you multiply it by a matrix that reduces the dimensionality, and then you get back to it, right? So that is that. Now, I will just go back and talk about this. In the context of let's say low. Uh, so anyway, this is the terminology we use for input. We use x, and we'll use z for the r squared, right? Now in autoencoders, z is often used. Also in GANs, z is often used for latent the latent variable. In for example, but you have to know that z is actually it's an activated z. It is the weight times the input with bias, the weights and bias applied, and then a nonlinear activation applied to that, which is unusual. If you remember, in the deep learning literature, the feed-forward literature, we would say that Z is just a weight W dot X plus B, and then we wouldn't then we would apply the activation to get the y hat or the output of that particular layer. So there's a slight difference in terminology in these two literatures that you should be aware of. I'm adhering to the terminology that is common here. So how do we do that? Suppose you have input and you have output, and you expect the same to go there, and you're representing it with the lower dimensional thing. So one sort of a very hand waving intuition I gave is, think of it as milk. Lots of milk, you have to transport it across the seas. You wouldn't want to transport it, all those gallons of milk. What you do instead is you dehydrate the milk into milk powder, right? And that is your sort of, it captures the essence of the milk. You transport that over to the other place, and then you de sort of rehydrate it back into milk, right? Without much loss, hopefully, of nutrients and so forth. It's a pretty successful approach. Um, so the same thing is the basic concept of autoencoders in many ways. Now, the principal component analysis is a special case in which there is no activation function, or identity activation function. So you apply a weight matrix here, you get the hidden variable, and the hidden variable, if you apply a different weight matrix, which is the transpose of it, you would end up getting back the original thing. Now, the thing is, in an autoencoder, in the simplest form, whatever you given, you expect to come out. And so your loss function is the gap between what you fed in and what you got out. So that's your basic autoencoder. You can write it by saying, if this is your loss function, you're looking for the argmin of WW prime such that the loss function gets minimized. So how would you do that? The normal technology of gradient descents, backprop, and everything kicks in. Nothing unusual here. Remember, at the end of the day, it is just a neural network. In fact, this is a dense net with single hidden layer. So it does work. And when you attach a complicated latent or an activation function, of course, now you have nonlinear distortions, nonlinear transforms, and you can do a much more complicated things. So for example, one interesting game you can play, and that is very effective, you take data and you add noise to it. You feed that in, and now you look at the response. What happens is when you look at the response and you look at the gap, not between the actual input, which was the initial image plus noise, but actually the gap just between the true image without noise and the output. And you optimize on that. You do a learning on that. So what will it do? The autoencoder learns to abstract out the epsilon, the noise from the picture. It learns to see behind the noise, right, at the actual picture. And that is quite a lovely thing, because now you have created a system that can denoise an image. Now once you have trained it, you can give images that have a certain degree of noise, pixelation, etc. It can fill it. Not only can you do that, for example, you can give it a letter with text on it, printed text or whatever, handwritten text, and it has creases and a coffee stain and so forth. And you can pass it through a denoising autoencoder, and it will remove the noise. It will remove the clutter in the background, and you expect a pristine page with writing to come out or text to come out, and it does so come out. Right? That is a huge value of denoising autoencoder. Then you can use it for something else. For example, what you do is you take image x, and then you apply a mask. So you have x plus mask. You deliberately put a random mask m somewhere in the picture. But when you feed it through while in the training process, you ask it to recover the actual image, fill in the gaps, right? So your loss function you still do between x minus y. So suppose y came out, y hat came out. Let me just write y because in this literature people just call it y or something. Let's say y came out. You still do this. So now what happens? You're basically asking it to get rid of that mask somehow and fill in the gaps. Now, the beautiful thing is it's able to do that quite often with a pretty good degree of success. Just goes to show the power of autoencoders. Now we take this one idea forward. So now and say that, see, let us not have just one hidden layers. Let us have a symmetric situation such that there may be many layers before the that bottleneck. They're converging to the bottleneck and then they're radiating out from the bottleneck, and you can have many layers so that you have the full power of a deep neural network. And the if you remember, a neural network is nothing but a function. At the end of the day, it is a function approximator. So you can still think of your deep layers before the latent layer, right, as some function f, and you think of g as another function now that takes the latent representation and produces G, right? So in other words, X goes to Z, the latent representation, using some function F, which is represented by the first part of the neural network, deep neural net, and it goes through G to produce Y, right? Which is the second part of the neural network. So this is F and this is G, right? F of X and G of Z. Yeah. Are we together? And so Y comes out and X goes in. So far, so good, guys. So now we put dense layers, many dense layers. But then you ask this question, can we do something better? For example, for images, why not use convolutions? We learned that convolutions are very useful. Let's put a lot of convolution layers instead. And so be it. Between the input and the latent layer, you can put deep layers, you can put convolutions, you can mix and match, you can do all sorts of crazy things. And so those are called convolutional autoencoders. Then there was a simple question to reflect on. We tend to create bottlenecks. What if we did not? What if we instead had the latent layer wider than the input and the output layer? So then you have to be a little bit careful. If you're not careful, what will happen is if there is no noise added or something like that, it will just learn to memorize the input and just pass it forward to the output. Right? So, which is why it is less common. But actually, there are situations where you do this. One situation, which I didn't cover in detail, is that somewhat counterintuitively, it tends to, you can come up with a sparse higher dimension representation of a input using this method. But you have to be a little bit careful. There's some implementation details and so forth. So those were autoencoders. The traditional autoencoders, they have a problem though. What they tend to do, two problems actually, is that the classes, right, they represent certain spaces in the latent factor space, right, certain regions of the latent factor space, right? And those regions sometimes overlap. And when they overlap, it's a little hard to tell. If you pick a point from here, are you looking at a 1, 3, 9? What are you looking at, right? Or which digit you're looking at, or what thing you're looking at, which class you're looking at. So that is one problem. The other thing that it doesn't quite deal with very well is if you randomly take a point in the latent factor space, right, and say, go move forward and just apply the GZ of it. This is Z point, and apply GZ to see Y. You will actually end up in trouble. You'll get some garbage because this point was never defined. There's nothing really here to move forward to. So that, in other words, the latent factor space has some blank holes to it. It's a very rough and ready way of saying it. Huh? So then there's this technology of variational encoders, which is little bit more complicated. It uses a variational inference argument. Um, what it says is that if you look at this, you're asking that given an input, what's the probability of seeing Z here? This is your quest. Given 8, what will the latent representation look like approximately? And when you use the Bayes theorem, then you get this expression in which the denominator, and this is only for those people who have taken engineering math with me, the denominator is intractable. Remember, this denominator, when we did Bayesian learning, was the source of trouble. One approach to deal with it was Monte Carlo. The other is variational inference. So a variational inference approach is not very magic. Is very straightforward actually. Once you get the hang of it, what you're basically saying is, you have these pieces. You don't know what they look like, right? X given Z. So what you do is you just approximate the distribution in the latent space, the distribution using some Gaussian. So what does it mean in very practical terms? Suppose there are only two classes. Just in the latent factor space, pick some points. Like it will end up being like this. Um, there'll be some Gaussians in the like a p-dimensional space, Gaussian hills that represent, let's say, suppose you have two things. Well, let's say the digit 1 and the digit 0. If that's the only thing you have, they will separate themselves out, and then more of them. And the only question, therefore, is if you make the hypothesis, what you're doing is you're projecting a hypothesis on the data. You're saying, what if this were true? Right? Then what sort of Gaussians would represent this, would approximate these this very complicated distribution that is truly there, but that I can't see, that is there, a good latent representation, but you have a problem to figure out what it is. Now, Gaussians, as you know, they're pretty nice things. I mean, they can approximate a lot of things, and they also belong to a class of exponentials that are themselves universal approximators. So they're very good actually in adapting to many, many functions very well, actually. So, especially when you see natural things like digits, you do expect that all the zeros will look essentially alike. So they should expect, or they should have a cluster of some form in the latent factor space. Right? So in that case, you just assume that what is that Q, a distribution of Gaussians, a mixture of Gaussians, right? That I can presume, or I can say that it is a good proxy for the reality. Now, if you think of the underlying latent factor space filled with Gaussians, right? One for each of those classes, or a mixture of Gaussians. Next comes a very interesting problem. All you have to do is Gaussian is completely described by the mu and the sigma, the mean and the covariance matrix. Sigma is the covariance matrix. Now, covariance matrix is something we talked about in ML100, but you may have forgotten. But if you remember covariance matrix, that is fine and good. In this situation, we'll simplify it even further. We assume nice well-shaped bell hills such that the only thing we care about is the diagonal, right? We just expect that the latent space correlations are approximately zero and the off diagonals, and it is just a diagonal matrix of um, of different variances along the different latent axes. Right? So if you do that, then you have a very nice way to figure it out. Now, to figure it out, there's a little bit of mathematics. We talked about information gain. What is the information gain? And the intuition we used is if somebody tells you something that's very likely, right? So um, let's take an example. Um, what is the likely? I mean, I give the example that the sun will come out in the east. Now, most of us don't doubt that. So suppose you're telling a friend that sun will come out in the east tomorrow, you're telling something that's pretty obvious. But if you, let's say that a highway tends to go under repair, and 10% of the time it's under repair, you tell your friend that, oh, there's a repair on the highway and there's congestion. So that is more information, because now your friend needs to hit the highway earlier in the day for commute, right? And suppose you give information about an even more unlikely event. Let's say that you say that there is a bridge that has gone under repair for some reason, and the likelihood of that was 1 in 1,000. Right? Once in 3 years, you have a situation in which maybe on the bridge one of the rivets or something struts somehow gets into a bad state and needs to be urgently or immediately fixed, and they close part of the bridge. That bridges are fundamentally bottlenecks, and then you do some repair on the bridge. You know what happens. We all have been in the Bay Area, so that is far more information, isn't it? The value of that information is high. So therefore the concept of information gain, how much information did your friend gain, it is essentially the inversely proportional to the probability of an event. In particular, you take the log of it, right? You give it a log. Now, log to what base? It depends which field you are in. If you're in information processing, information theory, you tend to take log base too, because there most of the information you look at is bits and bytes, bits, zeros and ones. Doesn't matter. Machine learning people and physicists, they tend to take the log to the base e, the natural log. The two are related, it doesn't matter, just by a constant. So which one you pick doesn't matter very much. So suppose you get information, then the next question that comes is, let's say that you keep informing your friend because you wake up early in the morning, you listen to the radio, and then you tell him one statement about things. What is the average information that your friend is getting? Average is called expectation value of the information. How much information gain there is every averaged over a number of days. So that is the proportion of the events. It happens p times in general, and times the information from that, which is log p. So p log p summed over all values of the outcomes becomes a quantity called averaged information gain. Average information gain has a name, and the name is entropy. Right? So that is something. So in other words, this is your entropy, and it is, and obviously here, when I write it as this, I should also say that I over all values of probability. Obviously, I've skipped over some of the notation, xi, and probability of the outcome xi of all possible outcomes, right? Maybe I'll write it in big letters. Sigma, let me write it in big bold so that we tend not to forget it. Um, Sum over all possible outcomes. So suppose you have an outcome xi and its probability is pxi, so log pxi, right? Where x is whatever random variable. For example, whether tomorrow the road is free, the road is undergoing repair, or the road is undergoing drastic repair on the bridge itself. So maybe three outcomes and so forth. So you can play with those numbers. So that is entropy. And you say the word that people use is that, so this is the formula. Like if you remove the indexing and the summations, think of this as the entropy. Huh? You assume like the sigma, sometimes people forget about putting the sigmas there, the summation and so on and so forth there. Right? And there are situations, like for example, you may have a continuous variable, right? So what is the probability of some random variable which is continuous? Temperature tomorrow being something, right? And so what is the information gain if somebody told you what tomorrow noon temperature is going to be? Temperature is continuous. There are infinitely many options. So this summation will become an integral at that particular point. So things like that. But the one thing to remember is entropy, which is usually represented with an edge, is essentially the expectation value of the information gain. Are we together? That's all it is. Now what happens is, suppose you work with a certain amount of uh, information, so that when you draw from the data, when events happen, what happens is that you assume a distribution p. But let's say for anomalous reasons, the events are happening not the way you wanted. They're happening with a different distribution q, right? And then there is a divergence between what you expected and the information gain that is happening. So that is called the cross entropy. right? And this again is something, more details we keep for engineering math class to give you a good simple intuition for it. We drew some pictures, geometric pictures, if you recall, but I won't go into that geometric way of looking at it. But it's like if you have P in mind, but Q shows up, then what is the cross entropy? The cross entropy is a P log Q. Q is the information gain with the understanding that times it was supposed to happen. Right? So that's your cross entropy. Now, when you have the entropy of an event, P, and of course P is happening, the things are happening as you expected. And when you have P and Q, there is a gap between the two entropies, cross entropy and the entropy of P itself. And that is called the KL divergence. That gap is not symmetric because your expectation was P and then you started seeing Q, so it becomes a reference point that you're comparing it to. So that is your cross entropy. I won't go into it now. What is that related to in our variational autoencoders? The idea is that if you don't know this distribution and you just say that actually I don't know, but I'll just assume it's a bunch of Gaussians, right? A mixture of Gaussians, then comes an interesting thing. You want to decrease the divergence between Q and P. In other words, you want Q to imitate P as much as possible. And how would you do that? Well, quite literally, KL divergence becomes your loss function. You make the autoencoder learn in such a way that it minimizes the KL divergence. And then whatever parameters come out, what the parameters will come out, the mu and the sigma vectors, of the bell curves, what is the mean and what is the essentially the sigma vector, if you assume diagonal and no off diagonal elements of the covariance is 0. So this is what you get, right? So that is a summary, I hope, of what we did the last time, right? Just as a recap, a bell curve is
Ask one question.
Go ahead.
What is the difference between KL divergence and cross entropy loss?
What is the difference between that? See, the two are different. Cross entropy is, so anyway, let me do that. I think I did that at some point. Let's just do that. Let us say that, I'll give you a classic example. Let us say that you're writing a classifier, Classifier, some X vector goes in, and what comes out is a cow or a duck. Cow, duck. So pick one of these. Let us say that probability of cow, right? So I will take the random variable y to be, so y hat is suppose this machine, because at the last layer, if you remember, Nisarg, we put a softmax or either softmax for multiple variables or a sigmoid. You remember logistic regression,
Yep.
right? Logistic unit, activation unit. So what you end up is the probability. Let's choose the word for cow, probability of cow, right? So this is the probability of the cow, right? This is what you're getting. Now, what is it that you were expecting? When you're training the data, you know that this is either a cow or a duck. Let us say that you take instance x1 and it was actually a cow, and you produced a probability y hat is equal to 0. Pick a number between 0 and 1, Nisag.
0.8.
0.8. And let us say x2 was actually a duck. And now pick a probability of its being a cow that your machine predicts.
Well, it is 0.8, right?
No, for a duck.
Oh, for a duck. For
Yeah,
duck,
so if it is a duck,
0.82.
what is the probability that it's a cow? Let's say that you say that your machine is not yet well trained. I'll just put it like this, 0.5, right? A duck, it is still saying y hat is the probability of a cow, remember, right? So hopefully your machine has
Oh,
learned
my head is the probability of it.
cow. So it is saying a little bit, a number smaller than 8. But see, now the cross entropy, let us think. We associated cow to 1. What should have come out? The answer that we expected for cow is what? 1 right? What is what should have been there? The label is saying cow. When the label says cow, what does it mean? Probability of cow is equal to 1, isn't it? That is the ground truth. Look at this situation. Would you agree that here the ground truth was the probability of cow was 1, right? Which is the y, the ground truth y, the label. And it is you are predicting a probability of 0.8. So do you see two different probabilities here? You can think of this as P and this as Q. The probability that you predict is Q. Are we together? And now think of cross entropy. See, what are you doing? When you write a term like this, minus P1, which is X1, is that Px1. So you can say P1, which is the cow, log y hat for the first. Let us just think about this. This is nothing but this is in terms of the language. If we consider this log y hat to be q, in the language that we are using, it is log q1. Are we together? If you identify as the other probability, this is what you are seeing, right? Q is that y hat is what comes out of your machine, and P is the ground truth. That these are two probabilities. Ground truth is the probability of cow should have been 1, and the probability of a duck should have been 0. But what you are seeing is Q. So now what happens is this, why do you consider a loss function with this? Why is the cross entropy a loss function? Let's take this. And likewise, let's go to the duck. What is the probability of a duck? It is 0, right? So you can say that 1 minus the probability of a duck, right, is 1 minus P2 times, which is the probability of a duck.
1 minus P1, right?
No, P2. The second data point is duck.
Oh, okay.
This one is actually a cow. This one is actually a duck, isn't it? So if you think P2 cow is equal to 0, isn't it? The ground truth is that it's a duck. So what is the ground truth probability that it's a cow? 0, right? So it is 1 minus P2 that is equal to 1, which is the probability of its being a duck, times the log, right? 1 minus Q2, right? Which is essentially the same as 1 minus y hat 2, right? So at this moment, ignore the second term, because you just look at this term, first term. What is it telling you? This number, cross entropy, what do you really want it to be?
0.
No, you want it to have the smallest possible value, right? The smallest possible
Yeah,
value
sure, the
would be
smallest possible.
minus P1 log P1, right?
Mhm.
At this point, right, the cross. So in other words, let's go back to it. Cross KL is equal to cross minus entropy, right? So think about this. Cross is equal to KL, right? The KL divergence, if you think about it this way, cross plus entropy, right? So what is KL? KL divergence is always a positive quantity. It's a measure of how different they are. It's never negative, right? So what is the smallest value the cross entropy can have? It can have the value of entropy itself, entropy P, the expected thing. Do you see that? If you go back to the definition of KL divergence, it is this. So the point is that the cross entropy is always more than the entropy, right? It can, as your learning takes place better and better, you want Q1 to 10 to P1, Q2 to 10 to P2, you want these matchings to happen. You see that, right? And that is what you're pursuing.
But um, but KL divisions itself is minus P log Q, right? Then
Yes,
how
yes,
is
it
it?
is. It is. See, KL is equal to minus P log Q. What is No, no, it is not minus P log Q. This is cross. This minus
Okay.
P log Q is the cross, right? And the KL is cross entropy minus entropy.
But the formula we saw earlier was just P minus P log Q for QM,
No, I did
wasn't it?
not. No, no, I did not. If you look at this. Look at this. This is called cross entropy.
Okay.
You see that, right? You got mixed
Oh,
up
I
between.
see.
You
Okay,
got
okay, okay.
mixed up between the two. Are we together now?
Mhm.
Right? That is it, guys. And so the point is, why do we use the uh, this thing? And now comes an interesting fact. Is it in some sense KL divergence? Are we minimizing KL divergence in even a binary classification problem? Yes, we are, because think about it this way: KL is cross minus entropy. So if you minimize KL, now entropy is going to be what? When the ground truth, the entropy of the ground truth is what? Zero. Like if the probability of a cow is one, what is the entropy?
Zero.
There is no information conveyed, right? If I tell you that a cow is a cow, right? So it's zero. So in a way, when you do the in classification, when you do the cross entropy, it is also equivalent to minimizing the KL divergence, minimizing the KL.
Can we call KL divergence as kind of a regularized cross entropy?
You don't use the word regularize. See, regularize is to dampen down the parameters of the model, right? They are absolutely equivalent. Whether you minimize cross entropy or minimize divergence, it's exactly the same loss function, right? But a KL divergence has a more general meaning when you look at a situation like this. When you look at an autoencoder, and for many large class of problems. So I'll give you a very basic example. See, suppose you take the height of 100 children, right? 1,000 kids that you randomly picked up. What will their heights look like? It will look like this, right? A bell curve. Or of people, it will look something like this. So this is your P. But suppose you went to an island and you notice that the island, this is the, the story Gulliver's Travel and the Land of the Lilliputians. Do you guys remember that story?
Lilliputians.
Yeah, Lilliputians. Yes. So we have, uh, suppose your distribution now of height is now like, let's say something like this, right? For whatever reason, your Lily, but with just a few people, very rare people being tall enough. So are you surprised by seeing this? If you were to do that, it would represent an element of surprise, isn't it? Yes, sir?
Yeah.
Right? And what KL divergence maps is, you realize that what you expect, and this is your Q, and KL divergence is therefore, right? Uh, it is basically the gap between P and Q. Actually, here it should be Q given P, but okay, Q given P. Right? How much surprised are you when you encounter Q, but you were expecting P? Right? And there are many variations of it. So, for example, you notice that if you take we all go through performance reviews in companies. It's the bane of it. Some manager sits and judges us and throws a number, and generally most people are. Some people feel happy. Some people feel dejected for at least a month, and then they leave the company. Actually, performance reviews can often is a causation of a lot of attrition. Is the bane of corporate life, right? So there you again expect that the average score. So suppose there's an average score of, I don't know, on a scale of 5, there's most people should get 3. Underperformer should get 2, and overperformer should get 4, and super achiever should get 5. But you go to a team and you suddenly find something like this, a distribution like the yellow one. what is that manager trying to say about the team? He's basically saying that this team is made up of intellectual Lilliputians, right? These are intellectual dwarfs, and he has no respect for the team. You should be surprised. How come um, the perception is so bad? And so things like that. So KL divergence is a very useful measure that you use to compare two distributions. It's not the only measure, by the way. We will talk about as we move into this course, and when we do networks and graphs and so forth, we'll talk about other divergences, right? And
So Asif, here the entropy is calculated based on what is expected or what
yes,
we
so you
encounter.
remember, so Nisarg, I went through quite fast, and so let us write it down. The entropy of an event associated with this is this of a let's say that entropy associated with a probability of some random variable, right, is essentially this pxi log pxi, probability of that event. Are we together? Right? It is by definition. In other words, it's not that entropy is equal to and somebody has computed this formula. This is the definition of entropy by definition. By definition, or another way to say that is entropy of Px is equal to the expectation value, statisticians write it with this unnecessary extra line through it. And so whenever you see it, you should know that you are doing expectation value of the information associated with Px, which is the same as expectation value of log Px. So this is literally by definition, you're defining it. You're not deriving it or something like that. You're just defining it.
It would be minus, right, in front of the
Oh, yes.
summation.
Yeah, minus. Yes, you're right. Expectation of the minus of the log of pxi. Great. Right?
No, in front of the summation, I think
Yeah. Here
expectation
also
is
and here also. Yes, you're
minus.
right. Yeah.
So I
Because
guess
information of px, remember, is again by definition minus log px. This identity holds. Yeah, forgive me for skipping a minus here and there.
so I guess in the best loss function we can achieve for KL divergence is twice the expectation of the expected value, negative in the
No,
negative
the
distribution.
KL divergence has this property, KL divergence, div, right? So KL, every KL has this property that it will be greater than equal to 0. Because remember, it is the gap between, again to state it, between cross entropy and entropy. Because this is always more than entropy. See, the clutter or the extra information that comes when you're surprised is more than the information when you're not surprised, isn't it?
Mhm.
Are we together? So let us take a probability distribution that on Jan 5th, or let's say Jan 15th, of every post-election year, you find a new president. That is your probability. But some year you find that Jan 15th has come or Jan 20th has come, but there is no new president. It's the same old president. That's a huge surprise, isn't it?
It's a nightmare.
Yeah. So that is your cross, that's sort of a sense of your cross entropy. Right? Why? Because that which happened quite different from what you expected. That's it. Right? When things happen, it's a measure of surprise, Nisarg. There's nothing fancy about it. It is just saying what is the gap between what you expected, which was P, and Q that you're seeing, what your data is showing you.
Yeah, it's just like it's both the expectations are distributed between cross entropy and entropy.
That's
Because
right.
entropy also has the P and cross entropy also has the P.
Yes. So P is your expectation, because if you're surprised with respect to some things that you expected to happen.
So the positiveness of this calculation comes from entropy, right? Because entropy is basically becoming high as a result of
That
which
is
the
right. There is more information. Entropy is a measure of information. There is more than you thought happening. What you thought happening was P. Now there's more than you thought happening, right? So you have one look at me and you expect me to go, suppose I were to go jogging, you expect half a mile should be it. One fine day, I come back with a 20-mile behind me of running. Would you be surprised? Would you feel that there's something really big going on?
Secret marathon trainer.
Yes, exactly. So you would want to know that. That's cross entropy, you know. Expectation is at most the probability that I'll reach 20 miles is zero, close to zero. But then suddenly I do that. Then I come back a changed man. And so now you have to worry that the every day the distances I run are different from the distances I used to run. And between the two, there's a cross entropy. Right? So in other words, you have to recalibrate your expectations then. So that's the idea of cross entropy. Guys, are we together? Is now, or do we have more questions on entropy, cross entropy, and KL divergence? KL
I
divergence is
think high
simply
level and yeah, I think I understood at the high level. I need to look at the references.
yes, you have to
Yeah.
read the book here. So one thing that we have to do, I'm giving you entryway into the concept, but it will solidify only when you go back and start reviewing the book. By the way, the deep learning book that you have, the one with flowers on it, does devote time to talking about entropy, cross entropy, and KL divergence. In one of the earliest chapters, I believe chapter 2. So please do go and review that. So, with that, is that a good summary, guys, or are we still feeling completely lost? See, here's the deal: the mathematics of variational encoders, if you didn't understand, remember it was an advanced topic. Ignore it. Just remember that there is a smarter way of doing, one rather powerful way of doing autoencoders is through using this generative methods by assuming a distribution. And when you assume a distribution and you figure it out, now you can sample from the distribution to create all sorts of output value. So what it means is you can, it becomes a generative model and you can produce all sorts of shapes, right? Example is you take a face of 100 people. In the lab, you'll do that. We'll take the faces of celebrities. And what we will do is we'll create completely new faces that are hybrids of those celebrities, right? That are not real people, but they're somewhere in between, and it's very interesting actually. Right? So we'll see that, and that's the power of a variational model. See, variational models and the generative models have this quality. Once you can train a generative model, now you can cook up data. And do you see the similarity between this and GANs? In GANs also, what do? There is a data distribution, P, the actual data distribution, right? Px. And what you're trying to do is you're trying to fake it with some Qx, the generator, right? And this is trying to catch up and infer the P. And sooner or later, it figures it out in the GAN. And something here is similar, except that it's not a GAN architecture. It's an autoencoder architecture. In both of these cases, you have a generative model. And generative models are great because you can create new data once you have trained them, very realistic new data with it. So far, so good, guys. So I've given the better part of how much time okay, what's the time now? I should keep the clock, 8 o'clock. We have given about 45 minutes to reviewing. I would like to take a very quick break of 5 minutes and we'll consider the review of last time over. Um, right. See, guys, if you understood the autoencoders but didn't understand the variational part, you're still doing very good. Variational will take a bit of time. You have to go review the book and you'll get it. Right. And then if you still don't understand, please come and sit with me, right, over the weekend. And I'll re-explain it to you. So guys, in my clock, it is 8:02. Let's meet at 8:07. All right, guys. One more minute.
Yeah, Asif.
Go ahead. Yes.
For the bottleneck was the wider latent features. So like we just gotta use really robust dropout, right?
No, it's not dropout. Dropout is different. See, dropout. See, dropout has to do with the loss surface. What it does is dropout introduces a lot of stochastic noise into the loss surface and prevents you from getting stuck in local minima. So imagine a loss surface that is sort of continuously sort of vibrating,
Right.
right? And it prevents you from getting stuck in local minimas. That's what it is. It does not have it to do. This is the actual representation. You're learning a representation, and therefore not to do with depends. You might even throw dropouts into your internal layers. May or may not matter. You're welcome to, but dropout does not have much to do with learning a latent representation. It's a different topic.
Okay. But how do you actually shake it up when there's more nodes in the middle?
How do you do what?
How do you make sure it doesn't just memorize all the observations?
Oh, it cannot. The moment you create a bottleneck, you realize that. So suppose I give you a story which is 1,000, like, 1,000 pages, and I ask you to summarize it in a sentence. there is no way you can just memorize it, right? So there is a joke. Somebody learned speed reading, and he was very good at it. He said he read the whole of War and Peace in 10 minutes. Somebody asked him, okay, tell me what is the story of the War and Peace. It's a very fat book. And he says it's simple. It's about a war in Russia, Napoleon's war in Russia. Right? So when you say that, it is about it, but a lot is lost also. But that is autoencoder. You can't just memorize it. Because nowhere in War and Peace the statement is there. This story is about Napoleon's war on Russia.
Hmm.
Right? So that's the difference. You can't memorize.
I think I'm talking about the one with like more nodes in the middle.
Yes, that can memorize. That will. In fact, that is the reason you have to be very careful. If you increase the number of the hidden layer, the bottleneck is not a bottleneck. It's in fact opening out, because then it will just trivially memorize it. It will just carry it forward. Doesn't not even memorize it. The identity, it will just forward the data, input data to the output. That's all.
How do you make sure it doesn't do that while still retaining that geometry?
That kind of geometry. Okay, so that brings us to the whole thing of sparse autoencoders. Let's take it offline. Huh? Today we have a lot to cover. I don't want to spend time on it because we are out of our break time.
Okay.
Yeah, let's do that. All right, guys. So I want to now. Are you guys seeing my writing screen?
Yes.
Yes. I'll start the recording again. Or you know what? I'll stop this recording. We'll call it the review of. Okay. Now I'll start a new recording, which will be for the material today. So we realize that a bottleneck principle gives you, or a method gives you good summarizations. And in a way, it is semantically, it's very rich with information, with knowledge, right? It learns when you summarize it, when you summarize something, you actually end up learning. So today, what I will do is apply the same concept, the bottleneck method, to word vectors, a representation of words as vector spaces, and see what we can do in creating more meaningful representations of words rather than the one-hot encoding. Right now, just to recap, if you have words, so let's recap of terminology. Let the vocabulary be V, of size V, right? This is the size of your vocabulary, right? Then one-hot encoding of a word is what? So suppose you have a word cat. What you do is you first create an index for every word in the dictionary. So ard, work, all the way to z something, right? So now you somewhere in there is a place for cat. You'll put 0 everywhere and put a 1 there and 0 everywhere. Then likewise, you have dog, and then, or zebra, let me just make it like that. So it's a little bit far off. Zebra, and that will be, and here is zebra, and here 0 here. Now this would be 0 everywhere and zebra location 1, right? And cat location all 0, 0, 0, 0, 0, 0, everywhere. This is now what are the problems with this representation? This is a very high dimensional space representation. Even so, something like 100K words, even if you take a modest vocabulary of 100K words, right? You're looking this vector, let me call the one-hot vector representation. I will use the same notation that I used with the bottleneck method. So remember the initial raw vectors we used to call X. So X belongs to word, for a given word, belongs to R to the power 100K. So imagine a Euclidean space that is 100,000 dimensions wide. It's a huge vector space. Now, there is another problem. If you take two words, any two words, xi, word one, word I, and word j, any two words, the dot product, what will it be? What is the dot product or the distance between these two words? Anybody? If you do a dot product between these two vectors, for cat and zebra, x cat and x zebra,
Always zero.
always zero, right? It is always zero. Why? Because every two, in other words, xwi is perpendicular always to xwj for all I not equal to j, isn't it? So you have no sense if every word is orthogonal to every other word, then there is no way that you can talk about the similarity of words. And yet, words don't exist in random orders. The words are pieces of communication and the building blocks of a natural language. They're parts of sentences. Certain sentences make sense and certain sentences don't make sense, right? So, and certain kinds of sentences occur quite often and certain don't occur that often. So we may search for a latent space, a latent representation, once again, a Z, right? Somehow, let's use a bottleneck method and build a theory of discovering that. So suppose you have this is your X vector. It goes down somehow through many things, whatever things you want to do. But actually in this world, it's quite simple. You don't do anything very complicated. Z, that's the beauty of it. So suppose there's a Z vector. For each of the words, there is a Zi vector here, right? That you can represent it as, right? Now the bottleneck principle is this goes into what it goes, and this is where it differs from the basic autoencoder. Something else comes out. So let me just call it Yi. Yi comes out, right? And we'll talk a little bit about Yi. But what we want, what are the desirables? So what are the goals that we want to set? Goals we want to set, that if words are related, they should be close to each, isn't it? So let me just for simplification say that all of these Z vectors are unit vectors for the time being. Then, in other words, they are just points in a sphere. This is Z1, this is Z2 in some hidden sphere, right? Z2, and basically you would agree that two words which are close by, they should have a smaller angle between them. For unit vectors, the angle between them or the similarity is easily captured with just the dot product, right? Two words, and what you want is, and for reasons, I mean, that if two words are similar, then their dot product should be big. The dot product will go, let's say, from 0 to 1, right, in the interval. It should be closer to 1, right? So for example, the word cow, or I don't know, the word cow and duck should be closer to each other, both being animals that you find in a meadow, versus cow and something completely different. Let's say a politician, because you don't tend to find politicians in a meadow or something like that. Or I don't know, some rocket, right? A rocket spaceship. You don't tend to find rocket spaceships in a meadow unless you believe in aliens.
So one quick question here, Asif, for our understanding, right? So when we say in terms of the intuition for understanding similarity here,
Yeah.
it could be anything, right? In if it's a language, synonyms are similar, antonyms are also similar because the relationship is opposite.
Yes, exactly.
Right?
So synonyms and antonyms are not that different, but unrelated word, like for example, you're talking of zebra and you bring in a hammer, right? Then they're unrelated. They should be far off.
Okay.
That's how it is.
Yeah.
So
So
the
the notion of
similarity,
similarity is very general here.
very general, but now we will give it a specific meaning now, right? So there is a statement which was back to the 1920s, I think 1926, by a famous person, I'm forgetting. He made an interesting statement, which all the new things are based on. The statement is, a word is can be defined defined by, or maybe the word is something else, represented by or something. This word, I'm a little foggy about the exact word, by the company it keeps. This is a famous statement. I wish I could remember the author, if anyone of you have it. If you Google it up, it'll show up in a moment. The exact statement. A word is defined or is understood by the company it keeps. With other words, where in the corpus. So let's go back to our statement. See, we assume in the background that there is a corpus which is a matrix of what? Documents, d1, dn, and each document is a vector, right? Some vector. I will just leave it as x, right? x1, xn. At this moment, you can take the vector in the initial space, one hot encoding space. So these things. Now what happens is that in this thing, there are lots of words. Each document has words that do or do not occur. So for example, cow and duck are present in this document. Right. In another document, DJ, there may be some other words that are present. So for example, the words would be auto encoder, right? And then you can use it for, let us say, denoising, denoise. Just by looking at the fact that they tend to occur, what words a thing tends to occur with. So suppose you had never heard of a cow, right? You just scan through all the documents of your corpus, and in each document, see what are the words proximal to the word. So suppose you take a word cow, take a word cow, word, say cow, that you want to get a sense of. Let's say represent it by X cow. How would you get to know what should it be similar to? So you go and look at the document and you take a certain window, right? Or you may not take a certain window, depends upon it. You just say, what does it co-occur with? What company is it keeping? And now we'll define the company that it keeps. Company does it keep. So you realize that if you read a lot of documents, you have never encountered a cow, the word cow, but you read a lot of documents where there are words which you do understand, and you find the word cow next to those words. Gradually, will you get a sense of the meaning of cow?
Yes.
Right? You'll get at least a pretty good approximation to what is meant by cow. So that is meant. And so we need to, the crucial thing is the company. And so there are a class of algorithms. They are bottlenecks like this. They help you create a latent representation of words, and they all are based on the concept of finding the company that a word keeps. Right? But how do you define company? The word company, in a little bit more mathematical way, is co-occurrence. 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 Now, co-occurrence itself is co-occurrence means two things exist in a sentence. So suppose I give you a sentence, they co-occur. You say that they're co-occurring in a sentence. So now the co-occurrence can be measured in many ways. For example, if two words are present in a document together, even though they may be at the beginning and end of a document, you may call it as co-occurrence. Or you may say that, no, words, a cow, it must exist within a certain window. So cow, look at the word before and the word after. So you take a window, sliding window, So literally, you look at the immediate company of the words, isn't it? When you look at the immediate company of a word, W, I, are we together? So suppose you take a window size 5. You look at the two words, the happy cow jumped over, jumped over the moon, right? I tend to keep taking this sentence. So the word cow, happy is there, jumped is there. If nothing else, you realize that whatever this thing is, this cow thing is, it can have happiness or associated with it. It can have the jump verb action associated with it. You begin to get a sense, and then you read more and more sentences. Am I making sense, guys? Yeah, this is a very obvious thing, right? So far, like pick a sliding window, pick a word. So given a word X, cow, find the couple of words before and a couple of words after, and you can choose, take an odd number, like pick an even size here, 2, 2. So the total size would be 5, or take it 4, 4, then it will be 9 or 7. People play around with different window sizes, depending upon what you defined the window size, or what do you consider company, right? The company of a word, how far are you willing to go away from the word? It's a matter of choice. Think of it as a hyperparameter of your model. But you can ultimately translate this famous sentence in many, many ways. So the some of the classic ways that it has been interpreted, and we'll go and talk about it, are first is uh, three very related ways. They are all in the family of word to vec, right? So those are the SIBO, right? Continuous bag of words. So when this thing is coming up, I'll explain what this means, guys. We'll come to it in a moment. A bag of words. The other one is skipgram, right? Skipgram is literally skipgram. No, people don't shorten it as SG or something. And the last one is called fast text, which is in the same family as word to vec, though it's sometimes people consider it a different algorithm. And it uses, the interesting thing that it does is it doesn't use word, but it uses sort of word components, parts. In an interesting way. We'll talk about it. But they're all very related algorithms, right? Then there is another algorithm which is called GLOVE with a capital V. So think of it as a global vector, glove, right? Glove, and you think of it as a global vector. In other words, it's a vector derived from a little bit more broad study of documents. So what I'm going to do now is give you the intuition. All of these intuitions are based upon a co-occurrence within a window. Guys, I'm getting a lot of background sound of somebody washing dishes or something. Could you please mute yourself? So how do we deal with, what are these algorithms? Remember, these are just different implementations of the basic idea that a word is pretty much understood or can be understood in terms of the company that it keeps with other words in the document. And you can define company with a sliding window. Pick your sliding window size and look into the sliding window size, right? The rest are implementation details, right? And now how it is implemented using the bottleneck, let's connect the dots. So what you say is that, let us say that let's take a simple way, right? You take a word like the happy cow jumped over the moon in joy, right? Something like this. Let's take a sliding window of size 5. And let's say that the word that you care about is cow. Right? So one thing you can do is you can create a table, sort of an input vector, input data space. So method one, you could create basically the happy jumped over. So this is your x1, x2, x3, x4, and this is your feature space, and a target, your y is the word cow, right? Then you can move your sliding window one step forward. And now sliding window number one, sliding window number two. Now what can you do? You can again go back and say, all right, what is the crucial word now for sliding window two? What is the middle word, guys?
Cow. You slid it, it's jumped.
Jumped. It's jumped, right? So in the second one, you now will say again the happy cow. The is gone. Happy cow over the, and the word here is jumped. Are we together, guys? Cow jumped, right? So, and you can keep sliding the window. One easy way to do that is from the third word, keep computing forward. Jumped over the moon. And the word is, you think of this word, the word that you're studying. And this you call the context. In some sense, it is the context. It is the company that the word is keeping. Are we together? So now let's take this example, the third one. Could you guys tell me what should be the, for over, what should be the words? What should be the context?
Cow jumped the moon.
Cow jumped, great. Jumped the moon. Now look at this problem. Now let's try to, and so you can keep going on. And so what you have is context and the word. And we are saying, if I give you the context, can you tell me what word it is? Right? So think of it as a classification problem in some sense. I give you the context and you have to tell me the why, the output, what word should be here. How do we do that? You can do that in a few ways. Now let's into our bottleneck, because we want to use our lovely bottleneck here, right? So there is an input, X goes in and Y comes out, right? And there is an internal representation of this. So what you do is something interesting. You take the first, you see that this is actually made up of, it's a four-dimensional vector here, right? The first row of data. Why is it a four-dimensional vector? I mean, at least four words are there. And each word is, of course, a 100,000 dimensional vector. So what you can do is you take the vector, the X of the plus X of happy plus X of jumped, you know, the one hot encoding, the input vectors, plus X over, you add them, right? You can just sum it, or some people prefer to average it, average of the four. So what will you end up with? The amount will still be, let me just call it, it will be the input to the word cow, right? It is the input to, it is the overall input in this sentence to the word cow. Do you understand it? That this is the context. If you add all the context vector, you're basically saying that this is the company, that it represents the context of cow. Cow context. So far, so good, guys? I'm just adding those vectors. In other words, it's a simple count vector at this particular moment for you. Any feedback, guys? Is this simple? I'm not doing anything fancy here. Anybody who's confused, please speak up.
This is SIBO, right?
Yeah, I'll come to that. I'll come to the names in a moment. But are we understanding the concept? All I'm doing is adding up their raw one hot encoded vectors of the neighboring words. That is what goes in here, right? This thing, this is your X that goes in here. And what you do is you force it to learn the weights in such a way, and W prime, you force it to learn these weights in such a way that Y that comes out is cow. The X for the cow, the vector one hot encoding output is one hot encoding for cow. So let's think about it. This is what is the space of this vector? This vector belongs to what dimensional space? If your vocabulary is 100K, what is the size of this space? In what space does this X vector exist, guys?
100K dimension.
100K, right? And likewise, what you expect, the word cow is encoded as again a one hot vector. It will belong to, again, 100K space. And do you notice that this is very reminiscent of autoencoders, except that you're getting something else out. You're feeding in X, which is the average of the neighboring words, and you're expecting a Y, right? Your Y hat that you are expecting, or let me just say Y hat that you're expecting is again that. But what you're doing is your architecture is such that you have a single hidden layer here, and you're forcing it to go through this bottleneck. Right, but how do you train these weights? The question is, that is all fancy, but I can just spill out some random weights. It would still work. Then the question is, what is the preferred weight of these objects? So the preferred weight that you have, and that is the learning part. Where is the learning, deep learning part? The deep learning part is given two words, xi, zi, zj, and remember I use this for dot product, should be closer to, it should be high for similar words. At the end of it, all the words that are sort of similar, they should ultimately come closer, but you don't try for that. Your loss function is that you expected cow and what came out. Now, what came out, so this is your ultimate goal. Huh? This is your ultimate goal. You somehow want to learn, but in this architecture, how do you learn it? You got the word, you expect the word cow, but let us say, what will you get here? Let's think through this. What you will get is, let's think through this. You have the W matrix, these are the weights, they hit the input. So you get X dot W. Now you get Z is equal to W dot X. Actually, there's a transpose, but let me gloss over the transpose. What's the transpose here or there? So we take the Z, and then what happens is that on top of it, we apply this. But then there is a node here. It's a value. We need to figure out which animal. Each word corresponds to, this one corresponds to ard, wark. This one corresponds to ZZZ. Somewhere in there is a cow. Somewhere in there is a zebra, right? What you get are certain numbers. These are called energies. When you multiply this with this, you get something, some numbers. Energies vector, which is again belonging to R 100K. You'll get some numbers come out. What you want to do is you want to somehow convert these energies to probability, and that probability, and then you want to check what was the probability of the cow. Now, if you expected a cow and you didn't get a cow, what is the cross entropy? Right? It is your log P cow that comes out. By the way, how do you convert these energies to this? We covered this in a previous topic. You soft max it, right? So if you have a bunch of numbers, x1, let me not use x because x is for input, a1, a2, an. One easy way to do that is first convert it to proportions. That is a1 over total, a2 over total, right? You can do that. That is one way of doing it. But you can do actually, but the problem is, suppose if some of them are negative and some are positive, then it begins to get problematic. Probabilities are never negative. So now you get a bit screwed. And so you say, okay, what can I do now? Better. So you say, no, I won't do this. I would instead take a clever trick. I will exponentiate each of these things, A2. And if I exponentiate, I get two possible benefits actually, mathematically, and then divided by the total of the x. So this is it. And then I can convert them into proportions by first you exponentiate it, and the next step you do is you sort of scale it down by the total. So each number, so let us say each value, e to the ai divided by sum of all of these things, aj. All of these numbers you add up, total, right? Total, the new total t prime is equal to e to the a1 plus e to the a2, all of these numbers, e to the an, this is your t prime. And all you're saying is that the probability, because now I have all positive numbers, and if I take a positive number and let's say probability of the event ai, of energy I, or the cow, or whatever class it is, ci, is this divided by t prime. In other words, it is this divided by equal to e to the ai, the energy produced here by sum of all of these energies, e to the ai energies, aj, actually, aj. So this is the probability that you'll see whatever it is, aardvark or cow or zebra or whatever it is. So you can take any bunch of numbers, any so long as it is finite, and you can convert it by going through the softmax process, right? Exponentiate it, and then just take the proportions, you will get probabilities. So now comes interesting thing. We talked about cross entropy and all of those things now. Now what can I do? I wanted a probability 1 for cow, 0 for everything else. But suppose I got P cow outside, I got a number something like 0.2, or very low likelihood, 0 point, actually it will be something like 10, because there are so many words, 10 to the minus 4. And it seems to be smaller. Let's say that the P of hammer, P of hammer is more. Let's say that it is equal to 3.1 into 10 to the minus 2, or something like that. Hammer seems the most likely, right? So these are small numbers, and let's say that the hammer seems more likely. Then you realize that, oh gosh, this is not what you expected, because you'd never hear that the happy hammer jumped over the moon in joy. That doesn't make sense. So you don't want hammer, you want cow. So what can you do? Cross entropy laws. You can do your cross entropy laws, guys, and then you can back propagate from there. The standard deep learning is simple back propagations. You shake up the weights, W and W prime, to make it a little bit better, so that in the next iteration, next mini batch, when it goes through, the cross entropy loss is a little bit less. This is standard thing that you learn for classification and so on and so forth, right? Are we together, guys? I'm not talking about anything extraordinary here. Am I making sense?
Yes, sir.
Yeah, this is very easy, right? And so what you do, you do epochs after epochs with batches of mini batches of data, and all of your data is fulfilling the condition that take a word and take its company. The company is the input, either averaged or summed, and the output is the word. And you make sure that this, somewhat like an autoencoder, this bottleneck architecture takes the input, context is input, and produces the word as the highest probability thing, the softmax. It's pointing to the word, right? So one of the nice things that exponentiation does, by the way, in softmax is it also exaggerates the biggest value, because if you think about exponentiation is a curve like this. So big values get extraordinarily amplified, and so their probabilities tend to become much larger, right? So that is that. Right? So so that is that. Now you can train it. When you do that, this particular method one is called CBAW. CBAW. Continuous bag of words, right?
So, Asif, can you take a moment to go back to what was back propagated?
Like, what was back propagated? So you
error?
lost. It is your loss. You are trying to minimize this loss, right? The cross entropy loss, which is, what is it? Y log Y hat. You expected it to be cow.
Mm.
What you're getting is mostly you seem to be getting the y hat of cow is not equal to 1. You want the probability of, you want to maximize this, so you have a loss, and this loss you can back propagate. You can try to minimize by taking its gradient and back propagating, so that the next iteration, hopefully next time when you give it, when you expect a cow is a bit more likely. Your network has, you know, shaken up its weights, improved upon the values, and now you get a higher probability the next time around.
Okay. So in this
That's
case, it'll be only a single, when the expectation is that it'll be only one item, a cow, right?
yeah. So that is the loss. So yeah, exactly. It will be the word cow for that one input. Cow is the output. And then if you pass a mini batch of data, of course, if you do stochastic gradient descent, of course, you can learn one word by one word, right? Or one row by one row of data. Or if you do mini batch, then you can add up all your loss functions across the different words you're doing. But those are minor details. Think that you're just doing stochastic, one word at a time. You get the intuition more easily. And you just back propagate. You go fudge your weights in such a way that things now, next time around, a cow looks a little bit more like a cow, right? So it may jump from from a hammer to, let's say, next it may start pointing to a zebra, which is closer, then to a horse, and then maybe finally to a cow with luck, right? In a few iterations. So that is it. So when you are done that, once you have a network that at least this network, at least for most words, most context, it can point to the word that should be there. What has happened? What has this network done? It is saying, if you give me the context, this box, if you give me the context, I'll tell you the word you're probably referring to, isn't it? So then when you think of that, think about this internal part. This network is fully trained. Look at the Z representation. There is a X vector for whatever it is, context, X context or whatever. Now here is a cow, word cow. And here is a Z. And you know that this is produced, forget about the input and the thing, once it is trained, somehow, whatever the Z, the hidden vector is of the cow, that when inflated up back into the 100K dimensional space using the W prime matrix and going through the, the basic softmax and the machinery of it, it will start pointing to X cow. It will begin to look very similar to X cow, isn't it? And that is, I mean, it produces energies pointing to X cow, right? Probabilities to that. So then what happens is this, therefore, has learned the representation of cow. But now suppose you didn't put only one word. One word is easy. You put the entire corpus and you kept on looking at the sliding windows of all the sentences and documents in the corpus. Eventually what will happen is, if it is getting all the words essentially right, given a context of a word, it is more or less pointing to the word. What have you learned? You have learned a good hidden representation of the entire vocabulary, right? And so that is the essence of continuous bag of words. Words. So this was the oldest way, BOW, of words. Now there is an alternative, which is the opposite, which does something quite different. It is called skipgram. Now let me perhaps use another color. It is called the skipgram model. Skipgram, but the full name should be skipgram with a negative sampling. And you'll see what. Now that looks quite a mouthful and a scary term, technical jargon. But actually,
Asif,
yes.
before we move forward, so where do we use the Z, the representation? Like
This is your word embedding. So hereafter, what happens? Given a word, given any word represented with a bag of, this one hot encoding, what can you do? You can pass it through this part, only this part, W. right? You can do w dot x, forget the transpose. There's a transpose sitting in there, but ignore it. You get z is equal to z, right? And z, therefore, what is the dimensionality of z? Depends on the bottleneck. How many, you pinched it down to how many. Typically, what you do is z typically is very common to make it 300 dimensional space, right? Or 500 dimensional space. That also is acceptable. Sometimes, if you have a limited vocabulary, you can even play with 50 or 100 or something like that. You can play with these numbers, huh? 50 for really small representation. And if you just think about what we did, we took 100,000 dimensional space and we reduced it down, let us say 100 dimensional space. So you realize that you have compressed it by a factor of 1,000, isn't it, guys? You have a much smaller vector space, which is only 100 dimensional compared to 100,000 dimensions.
So I understood that. What I don't understand is like initially we fed the context, right? And now you're saying we just feed one word to the Z.
Oh, yeah, yeah, yeah. Actually, sorry, I take that back. In this particular case, what happens is this is the relationship between Z and the word. This is the relationship here, right? You have these matrices, and with these matrices, what you can do is you can take a word and you can come up with one-to-one mapping between every word and its Z prime, Z vector.
So when we input a word, what will be the output in that case?
So you put cow and you'll get the Z cow.
So
Go
we'll get
backwards.
jumped over the moon as the output?
No.
No.
See, that is the context. Jumped over the moon is here. I'm saying if you take the word cow and you just look at this part of the situation,
Okay.
do you realize that there's just a matrix, linear matrix multiplication? You can use this to go back and find the latent representation Z. Suppose Y is equal to WX. Would it be fair to say that, okay, let me put it this way. X is equal to WZ, right? W prime Z. Would it be fair, therefore, to say that this is cow? This is cow. Would it therefore be reasonable to say that you can have Z cow is equal to W prime inverse X?
So that I understood, but what is Zika? What exactly is Zika? Isn't it the context
No, it is
representation?
not. See, at this particular moment, right, you throw away the left-hand side of the whole table, that matrix, because all you care is, if I want cow as the output, what is the input? What is Z? What is at the hidden layer? So suppose this part did not exist. This part did not exist now. Once it is fully trained, you realize that for every word that is produced, there is an internal Z representation connected by just a matrix.
Mm-hmm.
As simple as that, right?
So, so the use of this model is whatever word we feed in, the output would be the next word, or the output would be some other.
No, 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 no. See, while training, you use the context to predict the word, to produce the word. But once it is fully trained, so Nisarg, please differentiate between training and inference. Once you are fully trained, your weights are frozen permanently.
Mm-hmm.
Now look at this situation. What have you ended up with? You have created a relationship between a word and its embedding and its hidden representation.
What I don't understand is what is the use? Like, how is this going to be used?
Is
So
it
then you have to wait. That's exactly what I'm coming to.
Oh, okay.
dimensionality reduction is what I'm seeing. Asif.
Yeah, no, it has two main properties. See, guys, remember we started out this journey by saying that we want this representation. And the beautiful thing with this representation is Zi, Zj. This is not only, first of all, Z belongs to a much lower dimensional space, right? It belongs to just 300, let's say, dimensional space, much smaller dimensional space, right? Let me just put the word P here. P, where P is much, much less than original 100K, let's say, right? And the other thing that you start noticing, and this is an interesting thing that people started noticing, that you have a vector algebra or vector arithmetic here. This is what people started finding. And that is why this got a tremendous amount of attention, because things that followed from that is that you take two words which are really related. They are closer to one, let's just say. I won't put the exact value, closer to or bigger. Let me just say that bigger if the words are related, bigger if the words are similar. So the Z for those two words, the latent representation, or the word now I'll use is embedding. Embedding. The word embedding. The word embedding is Z. The Z that comes out for each of the words, it shows a very interesting relationship. Two words that are close to each other will have a good dot product, and two words which are unrelated will have close to zero dot product. That is one. The other interesting relationship people began to find is if you do this word king minus Z of man and plus Z of woman, you start getting approximately the value of Z for queen. And when people saw this sort of interesting vector arithmetic relationships, they began to get really excited. They thought they are onto something interesting, and they were, of course. The other thing that began to be like Z, let's say India minus Z, uh, let's say Delhi, New Delhi, is equal to Z of, let's say, UK minus Z of London. Do you see? So what it means is that in the vector space, somehow you have some words, India, right, and New Delhi, and then you have two words which are UK and London. And it turns out that the gap between these two words, right, the vector space, is exactly the same. Right? So not only are similar words close together, but they seem to have a very interesting word vector arithmetic to it. And this got people very, very excited, and people began to take the word embeddings very seriously. So guys, are we getting the main point? You can find a low dimensional representation of a word using this bottleneck method. Just think of it this way, that you can come up with a lower dimensional representation, which is a linear transformation. There's no activation function in the Z layer, hidden layer involved, just that, and you'll come back with the embedding. And all of these things are based on some form of co-occurrence or company, words company within a sliding window. Anybody who feels he understood, please speak up.
Yeah, I got it.
Got it, right? All of us. Anybody else got it?
Got it.
Yeah, got it, right? It's straightforward. And now comes this other algorithm, which is not a variation of it, which is actually far more effective than continuous bag of word. And it puts the thing on its head. It is skip gram with negative sampling. It just takes the continuous bag of word and turns it upside down. So let's go over the thing. The happy cow right? So when you look at this sentence, once again, let's go with a sliding window, pick an odd number sliding, even number on the left and the right, right? So let me take this again, the sliding window here. So this time what we do is we put the context, the real word on the left-hand side. We make it the predictor. It is your X. We put the cow here, and then we say, Balaji, can you please mute yourself? Yeah. The cow happy, cow jumped, cow over, right? So what we did is, we are basically saying that the word cow, these are the company, we have evidence that cow is keeping a company with these words. Are we together? Right? And then what we do is we do negative sampling. We deliberately take, let's say, cow, and randomly pick a word from the vocabulary. All right. So, for example, the let us say that we take a word, a DC motor, cow, and cow, and what should I say? Paper towel, cow, paper towel. If it were a one word, actually these are two words, so I'm a bit hesitant. But okay, the notion is the same: cow and what should I say? Hammer. Words that are completely unrelated, you throw into the mix. And then what you do is you create a table. You say that my prediction should be this cow does keep the company of the word the. So this is true. 1 1 1 1 0 0 0, and all the you throw in a lot of cow with random values from the vocabulary, right? So, for example, I don't know. Take up a very random word. For example, autoencoder. Very unlikely that these two words would be in the same sentence, except here. Right? So 0. You're saying the problem. It is, I'm creating a data set where the Y is whether or not there is evidence that these two words coexisted or co-occurred. So cow and the did co-occur. Cow happy co-occurred. Cow DC motor didn't co-occur. Cow autoencoder did not co-occur. Right. So this is your X1, X2. Are we together? Now what can you do, guys? What you can do is go back to your autoencoder, and now this time I'll be brief. What's the time? Time check, 9 o'clock. Okay, so it's time almost for a little bit of a break. So what you do is you feed in only the word cow, and then you let the results come out. You'll get these probabilities, right? Softmax. And what you want to do is you want to make sure that the probabilities of the probability of happy, probability of jumped, probability of over, these are high. And at the same time, you train the network, the neural net, or your weights, again, W prime, in such a way that the probabilities of, in this particular situation with cow as input, probability of DC motor, of paper towel, etc., of autoencoder is low. You want these probabilities to come out low. Are we together? So once again, you write your the same cross entropy laws, and then you start training the network. So visually what you're doing is, yes, see, in the first case, in the bag of words, you took 4 words of context, let us say 4 words of context, right? This, and you did some sort of a aggregate operation, maybe some average or whatever, to create a vector. You feed it into this, and you had one output, the word as the output, right? Context. In the case of skipgram, you turn the tables around, and what you have is a C bar. And in skipgram, turn the tables, and what you say is word is the input. What you want is the 4 words should start shining up. The probabilities of those, the context words, should light up. If you think of each probability value as how much that bulb is lighting up, you want those 4 words to light up and not other words to light up. Are we understanding it, guys? Huh? So this is an implementation detail. It just so turns out that when you use the skipgram model, you get much better results. There's nothing mysterious
Arthur,
about it. Yeah, go ahead.
uh, I mean, does it mean the probability should be close to 0.25 for those 4 words? Is that the expected probability? Uh,
No, this is only one sentence, no? That word cow may have in other sentences other probably other words in its company. But see, the bottom line is your idea is correct. If you take the sum total of all the words that tend to be near, that tend to form the context of the word cow in in the corpus of the documents, only their probability should be high. The probability of other things should be low.
okay.
That is it.
So Asif,
Yes.
so let's say we take the search engine for Google. When you type in your search key and it starts to show you suggestions, is that a skipgram?
The answer to that is the Google search engine uses more than 1,000 algorithms and approaches in a single query, and it returns in a couple of milliseconds. So one of the things, do they use word embeddings? Of course they use word embeddings. It's there. See, all machine learning is in a vector space, right? You need a vector space representation of words, otherwise it's meaningless. You can't do machine learning, right? So first state is you need a vector space representation of word. Second thing is, do they use this particular skipgram or not? um, I would say that the state of the art has moved forward. I would call these still, um, what I'm teaching you, it's a necessary thing to learn because it's very, very commonly used word to vec algorithm, both its implementation, CBOW and skipgram, and the third one, fast text, very commonly used. But we have moved ahead. The world of transformers has changed everything. So remember, we are going to get into transformers now, right, Patrick?
Okay, Asif. Yeah.
So I shouldn't disappoint you too soon that when transformers come, a lot of the things you don't use as much as with transformers. But the fact of the life is these word embeddings are massively used. There's a reason why Spacey comes with word vectors. So when you take a token, just do the vec underscore. You'll get the vector representation of the word. Right. And so they all come up with vector because similarity of words, you can do in one line. You can do document similarity in one line in Spacey just because of this, because you have a very nice vector space representation of word, which is semantically rich, right? Which contains that nearness and this nice vector algebra, the vector arithmetic to it. There is yet another implementation called fast text.
That's it.
Yes.
So this pairing with the unrelated word of cow, right?
Mhm.
There is some. Are those like infinite or
Yeah, infinite. So what you do is you don't do that. What you do is suppose you're taking a window size of so people, that's a hyperparameter of your model. Let's say I used to remember the number. Like suppose you find a word cow, and throughout the document you find let's say 100 words that it keeps company with, and then you might as well throw 100 words that it doesn't keep company with.
Okay, some random 100. Okay.
Yeah. Because it's always good to learn from balanced data sets.
Okay.
Right.
That's why probably is then the performance of the skipgram better compared to
Yes, actually the skipgram performs better in many ways because you not only teach what the word should be, what is the company it keeps, but you're also teaching the network the company that it does not keep. In some sense, there's a sort of an intuition on why it's slightly better. Actually, not slightly better, distinctly better, right?
Okay.
And then there is a fast text implementation. So what fast text does is it takes the word. So let's take the word. Um, let's take a long word. Hetero.
Sir, I have a question.
One second. Hold your question in mind. Let's take a long word. Heteroskedasticity. We encountered that in machine learning, right? You remember? It was the first big word we learned in our workshops. This word is very unlikely to be present in the corpus, or its probability will be very, very low. Are we together, guys? But this word hetero is quite common. Elasticity contains this, right? Skedastic is a word that can exist. So you start looking at word parts. or rather trigrams. What are trigrams? You break it up into little pieces. You know how to do that. And then you start looking at little combinations of characters. So trigrams of characters, for example. Right? So you may say het, right? Or you may look at ETE or things like that. And you start so hang on, I won't go into the machinery of it. Huh? Just think of it as that you look at specific word parts as bigrams, trigrams of, or some grams of characters in the word. And the same analysis that you did, you don't do with words themselves, but you do with these pieces or trigrams or pieces, character level combinations, character level n-grams within the words, right? And so, as you can imagine, this was, by the way, proposed by Facebook, I believe, in 2016. What it means is now you have a giant vocabulary. And so the training will be slower, but generally it will now outperform in many ways the previous algorithms. It's an improvement about over just using the words. So far, so good, guys. Right? So all of these come under the word2vec. Family. Any questions, guys?
So as
Yes.
if a word has multiple meanings, would that mean it would have different energies
That
also?
is the demerit of this. So for example, an Apple computer versus an Apple for the farmer have entirely different meanings, isn't it? So um, it is not context aware. That's a limitation of the classical methods that we are learning today. So the context aware things will get better into when we get into the transformers. Right?
See, thank you,
Now,
Asaf.
those are homonyms, a word that has many meanings. Right?
Not context aware.
Please say that again.
It's not context aware yet, right?
It's not, it is not picking up its meaning contextually. What will happen is, because you're making co-occurrences, the word apple will be proximal to computers. Apple will also be proximal to orange. And so what happens is that in your vector space representation, you'll have the peculiarity that apple is here, computer is here, orange is here, right? Whereas this computer should actually not be near, in one sense, near Apple, and in another sense, the two things should be that either Apple and computer are near, or Apple and orange are near, right? But both of the two shouldn't be true, isn't it? And that is the problem in creating static word embeddings like this, that they don't pick up meanings based on based on how it is used in a sentence. So ideally what we would want is that the same word, apple, the vector, the z vector for this in doc d1 should look like this, and the same z vector, apple, in doc d2. So let's say this is about farming, should look like this, and in this d2 it should look like this, something completely different. In the world of computers, computer world or IT world, it should look something different, right? And that is what you get when we get to the transformers later. But hold that thought in your mind. Today we are not getting there. We have one last one to do, glove. And by now you must be realizing that these are all very clever ideas on the co-occurrence matrix. So glove takes a very explicit approach. It creates a co-occurrence matrix. So you take a big giant matrix. You have the word cow. And again, you take a sliding window of whatever choice you have. If the word cow co-occurs with jumped, you go to the word jumped, and then you put a 1. And maybe you'll end up with 7 throughout the corpus. A cow jumped, and then the apple, orange, is 8, and some other things are 0, and some is 1. So you realize this is called the co-occurrence matrix. And here I shouldn't use the word. Actually, in the glove literature, they tend to use the word X for co-occurrence. So let me just use something else. Let me use M for co-occurrence. M for co-occurrence matrix. So guys, is the meaning of co-occurrence clear? Just slide over your entire corpus, and every time two words show up in the same window, just go increment the count at the intersection of those two words, right? So in this matrix, this square matrix, and this square matrix will be symmetric and positive, of course. All values will be, so in other words, the cow and jumped value here and jumped and cow value would be the same. Do you agree with that? It's a very simple statement I'm making. It's just a co-occurrence matrix.
Yes.
Straightforward. Now comes the interesting thought. What you do is you can convert this co-occurrence matrix to, so let me just take a much simpler matrix now. Huh? I'll make it not so big. I'll just say, suppose they're just four words, A, B, C, D. A, B, C, D, right? And let us say, actually, in the literature, they use the word X. Huh? So I will use the word X itself. Unfortunately, because just in the previous section, I used X for input, but the co-occurrence literature, I mean, this glove literature tends to use the word. So now if I say, what is the probability of seeing D show up next to A, right? So what you can do is, you can say, how often did A show up? Right? This is A, which is all the, how many times the word A occurred. Doesn't matter in the company of which other word. Would you agree that if I add up the columns, I'll get how often the word A occurred?
Yes.
Simple, right? If it occurred, A occurred with A itself, so cow, cow, right? And 3, 1, 9. So you can just add it up, right? And so let us do that bit of arithmetic. XA here is equal to 9, 10, 15, right? And XAD is the value here. What is that? 9 over 15. Are we together, guys? Am I making sense what XAD is? It's how many times did I see A and D together? 9 times. And how many times does A occur in this vocabulary at all? 15 times, right? There are 15 occurrences spread over A, B, C, D. So guys, I hope I'm saying something very simple and obvious. If not, then I haven't explained you properly. Somebody would like to speak up?
Yes,
Got it.
sir.
Yes, right. It's simple. So this is the probability of this word A and D occurring. That's the paper uses the word IJ, but I'll use A and D. The probability that AD will co-occur is this, right? Guys, does it make very basic sense? The probability of seeing A and D together in this is this.
Yes.
Given A, okay, let me state it different. Given A, finding D in the company of A, the probability is this. Right? Now it turns out that we want to use this somehow to go back and use in our matrix. We want to use this network again. Now I'll be a little bit fast because we seem to be running out of time. So let me just take ZA, ZB, right? What we want to do is we want to have this relationship ZA, and I won't give you the full mathematical details because I think we are reaching a point of mental saturation. ZAZB, we want the dot product, or in this particular case, we took D. We want it to be somehow dependent on how close these two words are. It should somehow be related to the probability of their co-occurring. Would you agree with this, guys?
Yes, sir. Yes.
Right. And now probabilities are positive, whereas this dot product might end up becoming negative. So what is one easy way not to ever be embarrassed by a negative number? We just dealt with it a bit ago.
What was it?
Exponentiate it. And so one rough way of saying it is that if I exponentiate the dot product, I will get this, right? And so if you work it, so if you take the log of both the sides, you will get ZA. And this part you can forget, guys. Huh? This is just giving you the intuition. D dot product is log P A D, and which can be broken up in terms of log X A D minus log XA. But you could have asked this question to keep it symmetric, like ZD, if you want to keep it like that to be the same thing. What happens is these things, you split it up into, you call it so-called bias terms, a bias of A and bias of D. So I'll leave it as that, a plus bias of D. You just break it up symmetrically into two pieces. It's just a technical mathematical thing. And so you come up with this lovely relationship, which basically says that the log of the co-occurrence, you don't even now need to do probabilities. Just go to your co-occurrence table, look at this number 9. Log of 9 should be the vector Z, A, vector D, D, plus, this negative comes to the other side, becomes plus, BA plus BD, bias terms, is equal to log of XAD. So ignore the bias terms. Basically, what we are saying is that the dot product between these two vectors should be like this. And so what is your loss function? You want this thing to be true, right? The co-occurrence, but you shake up your networks WW prime in such a way such that this thing is beginning to gets respected, right? You again the same thing. So create a loss and so on and so forth. So what will be the loss? It will literally be the gap between these two. This should be this. If it is not this, so suppose you take some vector, it is not yet fully learned. Then what happens? Your loss is literally the square of ZA ZD minus BA minus BD, and just square it, might as well, sum squared error, the typical sum squared error loss you're doing. And there is actually one more rarity factor, but let me just put, there's a factor here for rarity, decay factor, which you can for gloss over, let's say, for there's a reason, technical reason for putting a decay factor, but ignore it. So this is it, this is your loss function. Right. It is basically the sum squared error between what you expect and what you get when your model is not fully trained. Right. When you have some values that are not perfect, there'll be a gap between these two. And so all you need to do is square it and then move forward with it. So if you look at GLOVE, it's very interesting. GLOVE takes a more regression-like approach. It takes a sum squared error kind of approach. Where do you use sum squared error, guys, or mean squared error and so forth? You tend to use it in regression. Whereas the word to vec kind of thing, we tend to go more with a cross entropy, right? So this is the GLOVE thing. And here I've glossed over a few things, guys. So in order to explain it and not get lost into the details, I've glossed over a little bit. But this is the main argument. Do you see this, guys? It's a simple argument that you do. And I went over it a little bit fast, so you might have to watch the video again. Let me recap what I said. You look at the co-occurrence matrix, and if two things co-occur, A and D co-occur, they must be similar. It means that those word vectors must be similar. You apply that constraint, right? You basically say the dot product of XA and D must be somehow related to the probability of seeing them together. But probabilities are positive, and these vectors can be positive and negative. One easy way is just go exponentiate it. You'll always have positive numbers, right? And then what you do is you grind through the mathematics, and then you come up with some relationships, and there it is. And you also end up with the loss function. Right? This is GLOVE. Now, generally, GLOVE tends to, in my experience, quite often outperform word2vec. All the mutations of word2vec, CBOW, skipgram, fast text, GLOVE tends to quite often outperform, but not always. Consider the word embedding as a hyperparameter of your modeling process. Sometimes one can do better, but I tend to prefer the GLOVE by and large as a word embedding. So, all right, guys, today was a long session on theory, but I've finished all word embeddings. So next week we will do entire week on bottleneck methods. And just for the last 5 minutes, I'll throw in a sort of a bonus thing that you may or may not get. See, guys, if you go back and look at the bottleneck method, okay, let's say that you have a lot of data. You have good data, right? And you feed it through your some sort of a autoencoder, right? And you reproduce it, right? You create a reproducing encoder. So what will happen is this thing will learn. There'll be a abstract encoding that the network would have learned. You only show it good data. So and then suddenly you show it an anomaly, right? You give it an anomaly. Guess what will happen to the Z of the anomaly? It will begin to stand out, right? So we also use autoencoders in a very simple way for anomaly detection. But the important thing is don't train with anomaly data present, train with good data, and then feed in an anomalous data, and then your autoencoder will start observing and marking it as the anomaly, because that data point will stand out from the other data points in your latent space. Right? So therefore, you use this bottleneck methods, this autoencoders. They also help you with anomaly detection. Actually, they are a very powerful way of anomaly detection. Next week, we'll actually do anomaly detection also, along with all the other things we do with the bottlenecks, the word embeddings, reproducing images and generating images and all of those exercises. I think somebody was very interested in anomaly detection in this workshop. Who was it?
I was.
You were, yeah? Okay, nice. So there it is. We'll come to that. All right, guys. So that is all I have to say.
So, Asif,
Let's go back and review what we learned today. The new thing that
one quick thing before we move to the review,
Yes.
Asif. So,
Yes.
in all the intuition that you presented today, like with that the diagram that we were using, essentially the what's that the choke and the squeeze, right?
Bottleneck, yeah.
Yeah, the bottleneck. You were always referring to them with the notion of a word, right? So the Z we were trying to bring up was essentially a lower dimensional encoding of a word.
If you use word in the NLP case, but remember on Monday when we talked about it, we're talking in more general cases, no? Images and other things. It will find a lower dimensional representation for anything for you.
So what the way where I was leading to with my question was, I was looking for moving from that concept of a word to that of a document. How would you generalize this to a document?
Very good thought. So one of them is once you have the word embedding, a document is nothing but a total of the words. Add up the word vectors in the document and you get the document vector. That is one. And that is called document to vec, and people have been using it. But there is a further way that you can do it, which is we'll do when we come to transformers, and then we'll talk about such things as universal sentence encoders. Right?
Okay.
So we'll have more to say about it. See, the moment you start taking documents to mean a whole sentence or paragraphs and so forth, then there are many interesting things come out. See, guys, today I'm finishing what I would call the natural language processing with deep neural networks before the transformer came, right? Then the next 2 weeks, today is the 4th week.
I think third.
3rd week. This is the 3rd week, is it? Okay. All right. So if this is the 3rd week, it's a good point, because the rest half we will give to, next week again, 4th week will go just to the lab of this, and 5th and 6th week will just go to transformers. Now, I've introduced you to transformers in a practical way, but we'll go deeper into the transformers in the last 2 weeks. All right, guys. And we will also do transformers all over again when we do image processing, because now transformers are not just NLP, but they are in image processing also. So the transformers will end up getting a lot of time. They'll get time during the NLP part, and they'll get time during the image processing part 3.
Yeah, I have one question about that last topic, the globe vec. So, where did the BA and BD terms come from? So, sorry, I
Literally two
missed that.
words, no, two. So, okay, let's go over the reasoning again for glove. See, suppose you have a you have a corpus of only 4 words.
Right,
This is your co-occurrence matrix, isn't it?
right.
There'll be a certain, in a sliding window, there'll be certain co-occurrence of A, B, C, D, etc. That is it. Imagine a vocabulary of just A, B, C, D.
No, so if you scroll down a little bit,
Yes.
so I'm talking about that minus BA minus BD. So what
Oh, yeah.
does,
This is a technicality. Why log A is broken up into these 2 parts? There's a cute little argument. Ignore it. When you see BA, BD, imagine you're not seeing it at all. The whole argument is far more intuitive if you don't see it and you look at ZA, ZB, right? Plus something, doesn't matter what, up to a term, up to a constant. See, this is a constant, right? It's a bias term. Is basically log XAD. This part is intuitive, isn't it? If you ignore the constant part, which is
right?
BABD.
Okay,
Ignore the BABD because there's a little bit of a reason. You have to bring in arguments of symmetry and so forth. It will just take a bit of time and also add to the confusion. At this moment, I want to make sure that we stay with the highlights. We understand the big ideas.
okay, thank you.
But you see that this is very intuitive, Arithya, isn't it? It makes total sense. The dot product should be somehow related to the co-occurrence.
Yes,
That's it.
yes.
And that's that.
Okay.
And so you come up with the word embeddings, which is the glove word embedding. That's all it is.
So the loss function should be ZA ZD minus log XAD, right? You
Oh
took
my goodness.
minus.
Yes, yes, yes. Oh my, you absolutely are right. Thank you for catching that. D minus log XAD. My goodness, I would have lost that. Square, right? Is the gap between these two. Absolutely correct.
And can we say it's a constant? We can ignore the BA BD for brevity.
Yeah, generally what happens is those constants get learned in the learning process, right? Very
Right.
quickly the conversion they are learned in the learning process. It doesn't matter, basically. That's why you call them the bias terms. You just learn it as part of the whole game. Right? But do you notice how interesting it is? The loss function, the whole argument is very elegant. There's nothing very mysterious about the argument. It is ultimately using a sum squared loss. There is a little, see, there's always a little technicality to make things work well and take care of corner cases. So there's a decay factor involved, and obviously not to forget the summation symbol to sum over all data instances and so on and so forth. So, but at the end of the day, this is it. It's a sum squared loss. And that is glove. So guys, what did we learn today? Let me summarize. We learned, we are out of time. We learned that the bottleneck methods, when applied to NLP, give us word embeddings, right? There are 4 methods of word embeddings, 3 belonging to the word to vec category. They are continuous bag of words method, method 1, in which you give the context as input and the word as output, expect, right, from this whole bottleneck architecture. Then the opposite of it, skipgram, in which you give the word as input and you basically expect that all the context words will light up and the probabilities. The opposite of that. And remember, skipgram with negative sampling, right? Negative sampling is important. You have to also tell what is not the context. Right? And then there's the glove, which directly uses the co-occurrence matrix value, and it basically says that the exponentiation of the dot product is equal to the probability that A and D will co-occur. That is it. Yeah, that's simple statement. Exponential takes care of your positivity and so on and so forth. Right? And the dot product with unit vectors, max it will achieve is 1. Right? So there is obviously a little bit of normalization here and there. I won't go into that. Take that, constants and so forth.
Asif?
Yes.
For the loss function, should it be plus BA and BD?
Oh my goodness. Yes. Because I put plus here, right? Yes. Okay. I made too many mistakes. Good. Good. Since you guys are catching it, it shows that you're understanding it. Very good. So remember, guys, when I explain things, I'm rather careless with my proportionality constants and pluses and minuses. So be on the watch out and correct me.
Does the word skipgram has any meaning, sir? The word meaning as such.
No, I didn't get the question.
And the skipgram, like, does the word skipgram has any wordly meaning?
Oh, quite literally. No? In a n-gram, 5 gram, you skip the word, the central word, and all the other words are the context. See, the cow jumped over the, right? So what happens? If you take this taken out is your input. This is your x. And then the output is all of the rest of the, from the skip, this is a 5 gram, right?
Right.
You're skipping one. The rest of them all show up here. It's sort of a way of putting it. It's just a skip gram, right? The fact that you hide one, basically, one of the words, the center word.
Okay. Yeah,
That's
I
all.
was just guessing that. So
You can look it up, by the way. This is my interpretation. Maybe in the literature they have given even some better or deeper explanation of why it's called skipgram. I never questioned it. To me, the fact that there's one word being skipped always stayed in my mind. But there may be another reason. Look it up, guys. I may be wrong.
Thank you, sir.
Does it have like is it called like a 5 n-gram, like a 5 skip gram, or like skip 5 gram?
Maybe skip 5 gram, but nobody actually, you just call it the sliding window size. People don't use the word 5 gram, or they don't hyphenate it like that. At least I haven't seen it.
Okay.
And the window size, by the way, is the hyperparameter of your model. By changing it, you can get different results or different performances. Right. By the way, Pradeep, why don't you find that out? What is the root of the word skipgram? Let us all know next time. Huh?
Yes.
I'll learn something then. All right, guys, so I am done. Was it clear? Was the explanations clear, guys?
Yes, sir.
The big picture is you can use the bottleneck and the co-occurrence of words in Windows, and they're clever implementations of how to derive, the latent representations, and these latent representations in the NLP world we call the word embeddings, to come up with word embeddings. And we saw four implementation, 3 from the word2vec family, which was as continuous bag of words, skipgram, fast text, and then glove, which is a different one. Right. All right, guys. So with that, we will do the lab of all of this next time, of all the bottlenecks next week. And the week after that, we'll get into transformers. And transformers are big. Part 2 will have 2 weeks of transformers. Quite likely part 3 will have 2 weeks of transformers. So we'll have a whole lot of transformers everywhere. I'll stop the recording, guys.
Sir, I was just checking on Quora quickly, and it has same explanation like you told.
What I gave, huh? Okay, because you skip over there, a word in the n-gram. Nice, thank you. So guys, one thing, if you really want to take up the challenge, the argument that I gave, you can make it more precise. See if you can work out the steps of the math. It's very straightforward. That paper actually is a little bit dense. It's a bit hard to read. So, but I'm hoping that after this explanation, you'll find it straightforward to read. Okay? And so one interesting challenge would be you read the paper and you fill in the gaps, and also notice where did I screw up, if I did screw up somewhere. I tend to always get my signs wrong and forget the constants and so forth. As one professor of mine that I liked very much used to say, what is a constant here or there between friends? So, all right, guys. I wish you all a good night. Please review the book, guys. If you are not reviewing and reading the book, all this learning, it won't go deep. You need to back it up with the textbook reading. You have a wonderful textbook, read it, and you have the lab books, read those. And as a stretch goal, if you can go read the original papers on Word2Vec, etc., you should find it quite readable now. Read that. You go to medium.com and towards datascience.com, and you'll find gazillion articles on Word2Vec and Glove and all of that. Right? Read a few articles, different people's perspectives, you'll get the same explanation from different angles. So use whatever is convenient to you to review it or watch YouTube videos, whatever. But do review topics, guys. Make sure that whatever we study, you review. I know we are all busy, but if you don't review, then you'll forget. Mind is a leaky bucket. Things slip out. Thank you, guys.
Thanks
If anybody has